So yes, hello everyone, I'm Emily, I'm from the University of Sydney, and I, back home, am a radio astronomy observer. So today I'm going to talk about the project I've been doing here, putting some radio eyes onto simulated skies and looking at 21cm absorption of neutral hydrogen in SIMBA galaxies. So just to give you the big picture overview of what I'm interested in, it is in general gas in galaxies, which is responsible for everything from star formation to AGN filling and feedback and mediating the interactions on these different scales between the AGN and its host galaxy. Hydrogen, as the most abundant element in the universe, is of course a very big part of this gaseous picture of galaxies and their interactions. And in particular, I, as an observer, am interested in neutral hydrogen. So we just heard from Tamim a lot about the different phases of the ISM, and we see some of those different phases in neutral hydrogen specifically. So if we're looking very close to us at observations of our own galaxy, the Milky Way, or satellites like the SMC, we can get these very nice resolved maps of the gas in different phases. So we know that neutral hydrogen can be seen in the warm neutral phase, which is at a kinetic temperature of about 8,000 Kelvin, and that tends to exist in very diffuse large structures. We also know that we can see neutral hydrogen in the cool phase with kinetic temperatures on the order of 100 Kelvin or maybe a little bit higher, and this tends to cluster in very dense filaments or sheets. So in the nearby universe, we can see these nice resolved structures, but if we want to look at other galaxies, often it's very expensive and very technically difficult to get these nice resolved images of the gas. So instead, we typically rely on 1D spectra, like the ones you see here. So neutral hydrogen we can see in both emission and absorption under slightly different conditions. For emission, we typically are tracing the warm neutral medium, so the component at sort of thousands of Kelvin in terms of kinetic temperature. And we typically can only see it in nearby galaxies just because of the signal to noise required. Absorption, however, actually relies more strongly on the brightness of the background radio source that's lighting up the gas rather than the volume of gas itself. And so that means we can see it out to much further redshifts, up to a redshift of about 4. And we also know that it tends to probe the cold neutral medium. So again, kinetic temperatures of 100 Kelvin or so, and it tends to be clumping in much denser structures. For my observational science, I'm interested primarily in absorption. So we're looking at the cool neutral medium. And for this absorption, we can actually see it in 2 different types of scenarios. So in the first one, we have a background radio source, which is typically an AGN or a quasar. And the radio light from that AGN is passing through a galaxy somewhere along our line of sight. And we pick up the neutral hydrogen in absorption from that intervening galaxy. If it is an intervening case, we can often see the gas out to quite large impact parameters, which means that we can actually probe the CGM of these galaxies and start looking at group scale dynamics and kinematics. The other case we have for hydrogen absorption is we see it. The other case we have for neutral hydrogen in absorption is we see it towards associated systems. So this means that our radio AGN is in the same galaxy where the neutral hydrogen gas is doing the absorption. And that means that we can really probe very small length scales and look at the interactions between the AGN and the ISM of the host. So that's the big picture of neutral hydrogen in absorption. As I mentioned, back home I'm an observer and I'm working as part of the FLASH survey. Again, different to the FLASH code that Tamim talked about just before, just to confuse you all. So this is the first large absorption survey in H1. It's being conducted with one of the telescopes in Australia. And the idea is that we look at the entire southern sky like you see in this sky map on the right here. So all 30,000 square degrees or so. And for every radio source that we see in this sky, we want to see whether or not there is neutral hydrogen that we can see in it in absorption. Now, as you saw before, if we're looking very close to us, we can get nice resolved maps of the neutral hydrogen. But in FLASH, we're not looking close by. So our spatial resolution means that most of our sources look like this plot on the left here. We're basically looking at unresolved blobs. In terms of spectral resolution, though, we're actually quite good. At the redshifts we're interested in of about 0.4 to 1, we have what corresponds to about a 10 kilometer per second spectral resolution. So we get spectra like you see on this second plot on the left here, and so we can actually start to look at the shapes of these line profiles and maybe learn something about the kinematics of the gas that is doing the absorbing. So in terms of what we're getting in terms of scientific results from this survey, we have some of the data that's already out now, and we're starting to do science with it. If we look at the structure of these sources, as you saw from the continuum images, they're unresolved, so we can't tell a lot from that, but we can build up the spectral energy distribution of these sources. So we look at how their radio flux changes as a function of frequency. If we do that, we can look at some broad spectral shapes, and we can tell from these spectral shapes whether these sources are compact, like the diagram on the top here, where the radio jets have not yet broken out of the ISM of the host, or we can tell if they're extended and the jets are much larger, like some of these beautiful radio images that you see as splashes in the news, like you saw on the first slide of my presentation today. So we can do that for all of the detections we have so far, and we have done that. And we've actually found that about 60% of our detections in flash that have neutral hydrogen absorption are towards these compact sources where the radio jets haven't yet broken out of the ISM of the host. That's a bit unexpected, because if you take any given radio population, we would expect far fewer than 30%, maybe as low as 5 to 10% of this random sample of radio galaxies to have these very, very compact jets. So there's something strange going on here. And what we really want to know is why most detections in this survey that is untargeted, that is looking at every radio source in the sky, are towards these sources that are compact where the jets haven't broken out. It could be that we're seeing evidence of jet ISM interactions, which means that the neutral hydrogen gas is really popping out in these sources, or it could be some sort of selection effect that maybe we didn't think about when we were calling this an untargeted survey. And so that's really what brought me here to the CCA to work with Samuel and Stephanie. We came up with a project where we could use cosmological simulations to try and disentangle what was going on and understand these observations that we're starting to see. So we have this project, A Cool View of Radio AGN in Cosmological Simulations. And in the next couple of minutes, I'll step you through what we've done so far. So first, we need to make these simulated galaxies into radio galaxies, because in most cases, this can't be done off the shelf. So first, I want to convince you that cosmological simulations are the right tool to do this, as opposed to zoom-in simulations, which might be another alternative. Then I'm going to talk about how we can find the right galaxies out of these large boxes to call radio galaxies. And then I'm going to talk about how we actually go through the process of observing these galaxies to get data that matches our flash observations. And basically, we're going to turn our particle data that you see in that image on the left here into fairly low-resolution images like you see on the right. Then I'll go through some of the results that we're getting, trying to find out what's important in terms of detecting this neutral hydrogen in absorption. So I'll look at orientation effects, luminosity effects, the morphology of the jets that we're injecting, as well as the galaxy morphology. So first of all, cosmological simulations. So these are the right tool for the job. First of all, because they're big boxes and they're evolving over cosmic time. So that means that we get very, very interesting AGN galaxy and galaxy-galaxy interactions for a large sample of galaxies. That means that we can get large statistical samples of these sources, and we can start to do statistical comparisons with the large samples that we're getting as observers. And you can see up on the right here, I've got this nice video from Paco that shows some of the AGN feedback that's happening in the SIMBA simulations, which are the simulations that we chose to use. So a little bit more on SIMBA. SIMBA does have a cold ISM, but it is unresolved. That said, it's quite a good simulation to use for us because the H1 masses are calculated on the fly and they're done on a per particle basis, according to this prescription that's in the paper here that you can follow up if you're interested. The other great thing about SIMBA is there's already been some post-processing work or analytical work done by Thomas. They basically came up with some nice prescriptions for the SIMBA radio galaxies that allowed us to create quite neat samples from amongst the big box, again, pulling out specific galaxies to call radio galaxies. And with their prescriptions, they're actually able to show, as you can see in this plot on the bottom right here, that they can fairly accurately reproduce something called the local radioluminosity function. So basically, they say if you're careful about how you pick your galaxies out of this box, you can actually reproduce some nice observables just in terms of how bright your sample of galaxies is. So that's quite nice. That's good for us because, again, we ultimately want to match all of these findings to our observations. So in terms of finding the right galaxies, we have a big box that's evolved over cosmic time. We need to get specific galaxies out of it so that we can get statistics about the neutral hydrogen in them. So first of all, we picked a snapshot. That was easy. Flash looks at redshifts of between 0.4 and 1, so we just picked a snapshot of 0.4. Then we also wanted to make sure that we have neutral hydrogen-rich galaxies, which just allows us to focus on the question of how the distribution of gas in the galaxies affects our ability to detect it, rather than worrying about whether there was gas there to begin with or not. So the plot on the right here just shows the simple cuts in parameter space that we made, and the big circles highlight 16 galaxies that we selected basically at random to be our pilot sample for this study. We also made sure that these sources would be considered AGN hosts, again using the Thomas prescription. For experts, these are the parameters that we used, but you don't need to worry about those if you don't know what that means. So these are what our galaxies look like. We have 8 that are fairly nice, neat, disky galaxies, and 8 that are a little bit complex, maybe the result of mergers or interactions. So hopefully this means we've got a nice representative sample to do some interesting science with. So now we can actually think about how we observe these as radio astronomers. So we have our particle data from SIMBA. To that, we actually need to add static radio jets because there's no information already in the simulations about the radio emission. So we paint these jets on after the simulation has been run in post-processing, and the shape and brightness of them is essentially a free parameter. So once we decide on that, we then discretize the jets, split the flux up into different cells. For each of those cells or bins, we then do 3D ray tracing through the gas particles to get measures of absorption based on the particular line of sight that we're looking through towards the galaxy. So in terms of the physical parameters, we need to pick both the total radioluminosity of these jets that we're painting in, and we need to work out how much of this radioluminosity is being absorbed along any given ray. For the radioluminosity, we just draw sensible values from the local radioluminosity function. So this is an observer-based quantity. And then for the absorption, it's kind of like a very simplified form of radiative transfer. So we just calculate the optical depth based on the scattering cross-section, which takes into account the physics of neutral hydrogen, 21cm absorption, and we also need the column density of neutral hydrogen, which we get directly from the particle data. So that's how we create our radio observations. We also need to worry a little bit about the shape of these radio jets that we're injecting, and so we have 3 basic shapes that we're using here. The names FR0, 1, and 2 are just the names that observers would use for these kinds of shapes, and that's just to convince you that these are actually physically motivated. For this talk, I'll be focusing on the outer 2, mainly because, again, we're worried about this question of why we see so much H1 in the observations towards these compact sources that are confined and not yet broken out. So that's what we're going to focus on for the last couple of minutes of the talk. All right, the other thing we need to do now that we've put the jets into SIMBA, we need to make the data that we get out from SIMBA actually look like our flash observations. So to do that, Samuel and I have come up with a new pipeline called Sangria because we love our acronyms. And basically with this pipeline, we take our particle data with our injected jets, we put it through some convolution steps and pixelation steps so that we get it to look like what we get out of the flash survey. So to give you a comparison, our data on the left of the slide here is what we get from SIMBA galaxies with Sangria, and on the right is some real data that we get from the flash survey. So it looks pretty convincing to me. As an observer, I would trust that data on the left. So now the question is, if we use the same pipelines as we do as observers in the flash survey, do we over-detect H1 in these compact sources where the radio emission isn't broken out yet, or do we detect it more in extended ones? So first, we need to work out what actually influences these flash detections that we see, in this case, in the simulations in SIMBA. First of all, galaxy orientation. So basically, the long story short here is that galaxy orientation matters. If we put a compact radio source into any of our galaxies so that it is spherically symmetric, and we rotate the galaxy so that we're looking through different lines of sight, we actually see significant changes to the line profile. And hopefully, we now have a video that demonstrates just that. So you can see that as we rotate the galaxy through 360 degrees, we're just tracing through different lines of sight, tracing through different gas particles, different densities of gas. So the depth of our line profile goes up and down. To pull out some significant snapshots from this, we see that if we're looking edge onto the disk, we get the deepest line, which makes sense. We're looking through the most column of gas there, so we would expect the most absorption. If we are looking face onto the disk, we're going to get a much shallower line because, again, we're not looking through as many particles. Interestingly, here also, you actually see a little bit of a blue shifted component that's the wide wing in that line there. As an observer, that's quite interesting. That tells me that we've got some sort of outflow. And in this particular galaxy, we spent a long time looking at this. It's actually a very real physical phenomenon. There is some gas that's being kicked out by the AGN activity in the SIMBA simulations. So that's real physics that you're seeing there, which is quite nice, quite gratifying to see. But that's the takeaway. First of all, galaxy orientation does matter. It changes our column density along the line of sight. The next question is, does the intrinsic luminosity of these radio jets matter? So now, if we take one galaxy, again, rotate it through 360 degrees, but in addition to that, we change the radioluminosity that we're giving our compact jets, we want to do the same question again and see how our line profile changes. So here, instead of showing you individual line profiles for that big 2D space, we're just showing you for each individual snapshot of observation of a particular inclination of a galaxy and a particular brightness of the radio source, do we detect H1 or not? Basically, you can see here that radioluminosity has a very, very big impact. if we go above a certain threshold for pretty much any inclination angle, which corresponds to any column density in SIMBA, we do actually detect the H1. And pretty much below that single threshold, we don't detect it at all. So that's all very interesting, but this is just for a single galaxy, our good friend 164, a nice, neat, disky galaxy. So the next question you might be asking is, well, what happens if we try this for the full 16 pilot sample galaxies, including the ones that are complex mergery systems where the gas is all over the place? And the answer is, it continues to matter even if we look at our full pilot sample of 16 galaxies. So in this plot on the right here, again, same axes, radioluminosity on the y, column density on the x, which is a proxy for the angle of inclination that we change for each of these galaxies. And then each of the squares in our heat map is just colored by the detection fraction. So you can see that for observations where we have the most H1 and the brightest radio sources, we are pretty much always detecting the hydrogen that's there. So that's kind of nice to know. So radioluminosity does indeed make a difference. What about galaxy type? We have this sample where 8 of these galaxies are disky and 8 are complex mergers. So if we split this heat map up into different types of galaxies, we start to see maybe there's a little bit of a difference. So if I put lines onto this plot showing where all of the sources are detected in the disky side, and I can map that onto the complex side, you can see there's a difference of maybe 1 or 2 cells. Going back the other way, again, you see there's 1 or 2 cells different. But we need to remember that actually we're not uniformly sampling this space. So there are different amounts of observations in each of the bins. If we look at that, again, in terms of the number of observations we have in each bin, we actually see where there's a discrepancy sort of up here and over here. I've animated it. Excellent. We actually have very low number statistics. So it's probably not a significant difference when we're looking at the disk galaxies as opposed to the complex mergery galaxies. No significant effect. Final question, does radiomorphology matter? Because, of course, I wanted to know whether we're over-detecting compact sources because of something interesting about the source or because of some sort of selection effect. So we make the same sort of plot again, but on the left, we do it for the confined radio source, and for the right, we do it for the large breakout source. We add those lines again, and it looks like, yes, there is a significant difference. So it looks like we really are detecting neutral hydrogen very much towards the compact sources much more often than we are towards the extended sources. So to sum up then, it looks like Flash is more likely to detect neutral hydrogen when galaxies are closer to edge-on if they're disky, because we're probing a higher column density of gas, when the radio jets are brighter, just because we have a higher signal-to-noise, and when the jets are compact, simply because it looks like we're favoring geometry for backlighting the H1 when the jets haven't yet broken out of the ISM. In terms of future work, we'd like to tie the radio emission more specifically to the backhole fueling and feedback information that we have from SIMBA. We'd also like to make a Flash light cone so we can do a full observational snapshot like we would for Flash and look at 30 square degrees of the SIMBA sky. And of course, there are always fun things we could do with future instruments, so thinking about synergies with the SKA and NGVLA. And I think I will end it there.
All right, questions for Emily? Lucia?
Very cool. I'm curious to hear more about this first point, especially because it sounds like you just plop in your different types of jets. So, like, where might that not be an accurate thing? Have you thought about that for your different selection things?
Yeah, so it's a really good question. It's definitely something with a stretch goal for this project, and we didn't quite get there yet. So really with this project, we actually wanted to understand mainly how the galaxy orientation was affecting things, because that's not something we can change as observers. And for that, it really made sense that we could just treat the jet luminosity as a free parameter, because that meant we could keep the jet luminosity uniform across all of our sample and then just worry about the actual sort of morphology of the gas and how that was affecting our detections. But so this Thomas work did some nice things with SIMBA, basically used the Eddington fraction and the black hole accretion rate and used those to predict a reasonable radioluminosity for each of the individual galaxies. So our idea is our next step would be to use those same parameters and for each of our 16 galaxies give it a physically reasonable radioluminosity, and we could still vary the jet size but fix the luminosity and then see how that affects things.
Other questions? Yes, in the back.
Us with the heat map?
Yeah, that's the idea at the moment, yes.
Cool. I wonder if something to think about is how like two different parameters that you're analyzing in these heat maps might be correlated with each other in your construction of the data sets. And if it could be nice to use some like causal analysis tools to actually identify like which one of these factors are driving detection independent of like the variation in the other factors. And yeah, it's like it might be interesting. It might be surprising that you get some results that you don't that are counterintuitive given the plots that you generated there.
Yeah, that's a good point. So we probably do need to think a little bit more about how we're analyzing the results that we've got. So one thing I will say is one reason, again, that we kept the radioluminosity as a free parameter, it meant that we could fix things like the radioluminosity and just focus on how the galaxy orientation was changing things. Yeah. Whereas if we moved straight to the physical prescription for radio emission, that would have possibly led to surprising correlations that we wouldn't have been able to disentangle. So at the moment, we are trying to be quite careful to keep these things distinct. But I think you make a good point that maybe there is some more interesting analysis to be done just looking at the data we have. So,
sure.
Yeah.
Thanks.
Thank you.
All right, let's thank Emily again.